These are your notes on Graham's law of effusion, and these will start on the PowerPoint slides and then we'll move to the handout. So Graham's law of effusion, the rate of effusion of gases at the same temperature and pressure are inversely proportional to the square root of their molar masses. So it's easiest if you know the molar masses and if you know your compounds, put the smaller one on top. So when you're doing your math, it ends up on the bottom, and we can have a value greater than 1. So the rate of effusion A over the rate of effusion B is equal to the square root of the molar masses. We know that effusion is when a gas molecule moves through a tiny opening, so this is just looking at the rate of it. And do I know mathematically what each relates to? So if I'm looking here, I've got the rates of hydrogen and oxygen at the same temperature and pressure. First thing that we want to do is find the molar masses of both of those elements, diatomic elements, remember. So hydrogen weighs 2 grams per mole and oxygen weighs 32 grams per mole. Since I know the molar masses, I want to put the smaller one on top here, because then I know when I do my calculations, the value will be greater than 1. So my rate of effusion of hydrogen over the rate of effusion of oxygen is equal to the square root of the molar mass of oxygen over the square root of the molar mass of hydrogen. When I plug in my values, I take the square root of 32 divided by the square root of 2 to get 4. So there I know that hydrogen effuses 4 times faster than oxygen. So now what I want you to do is change to your handout slide on Graham's law, and we'll do some more practice problems. Okay, so hopefully you have your handout out. We're going to do the front page as practice, and then the back side we'll work on together. So Graham's law says that the gas will effuse at a rate that is inversely proportional to the square root of its molar masses. And again, we know that it's expressed like this, and just a reminder, and maybe it's worth writing down, it's easier to do this if you put the smaller number on top, and that way it gives us a rate greater than 1. So, our first practice problem, under the same conditions of temperature and pressure, how many times faster will hydrogen effuse compared to carbon dioxide? So we're going to take the rate of hydrogen over the rate of carbon dioxide, and remember I'm putting hydrogen on top because I know it's the smaller mass. When I find the mass of carbon dioxide, I know it's 44, over the mass of hydrogen, which is 2, and that gives me a value of 4.7. So I can say that hydrogen travels 4.7 times faster than carbon dioxide. The next question says, if carbon dioxide in problem 1 takes 32 seconds to effuse, how long will the hydrogen take? So we've got to think to ourselves, if carbon dioxide takes 32 seconds and hydrogen travels faster than carbon dioxide, am I going to multiply or divide my rate to figure out how fast or how long the hydrogen will take? Because hydrogen should move faster, and I know that carbon dioxide takes 32 seconds, hopefully you understand that we should have a division problem here to figure out that the hydrogen would move at 6.18 seconds because it moves 4.7 times faster than carbon dioxide. So number 3 problem says, what's the relative rate of diffusion of ammonia compared to helium? So does ammonia effuse faster or slower? So we know that since we know our compounds and elements, we're going to put helium on top because it's smaller. We know the mass of ammonia is 17 and the mass of helium is 4. When we do our calculations, I can see that helium moves 2.06 times faster than ammonia. And then to follow up question with number 4, very similar to number 2, if the helium in problem 3 takes 20 seconds to effuse, how long will ammonia take? Well, I know that the helium should move faster than the ammonia, and so I know helium moves and it takes 20 seconds. So in this one, I want to think about, is it a multiplication or division to find out how long the ammonia takes? Well, I know ammonia should take longer, and so I'm not going to divide on this one, I'm going to multiply the rate. And so 20 times 2.06 will give me 41.23 seconds. Alright, the last problem. So it's an unknown problem. On these ones, it's easiest to put the rate of the unknown on the bottom to start. So the rate of helium divided by the rate of the unknown is going to be equal to the mass of X over the mass of helium. I know my helium is equal to 4, so I'm going to say the square root of X over 4. And when I look at my problem, it says an unknown gas diffuses 0.25 times as fast as helium. So there's a couple different ways to solve this. The first one we're going to do is we're going to set it equal to 1 over 0.25 because it diffuses 0.25 times as fast as helium. When I do that, I know that it's equal to 1 over 4. Or I know it's equal to 4 because it's 1 over 0.25, and to do that math, it's equal to 4. So when I do my math here, I want to figure out to get x by itself, I'm going to simply square root or square both sides to get the square root away. and then I would simply solve for x. So once I do that, I'm going to have x over 4, which equals to 16, and then I'm going to multiply both sides by 4 to get the x by itself, which gives me 64. So let me go back here, that was a little fast. So here's the math to do that. So again, here's my problem. To get the x by itself, I would square both sides to get x over 4 equals 16. To get the x by itself again, I'm going to multiply this side by 4 and this side by 4, because 4 is a denominator, so that gives me x equals 64 grams per mole. So that's how we can figure out the unknown gas that diffuses 0.25 times as fast as helium. So it should be slower, so 0.25 times as fast means it's going to be slower. So the wording on that's a little kind of funky, but on the back side it should be pretty straightforward. So we're going to practice the back in class. Thanks for coming ready.